Okay. Okay, thank you. Thank you, Aditya. And welcome to this set of lectures, which will be about geomorphology and landform. And let me say that I'm agreeing to the recording. Okay. And those lectures will be about geomorphology in general. And what I will try to do is to give you examples that are relevant to Indonesia and also example from Indonesia. So geomorphology has a lot of different topics, and we could talk about glacier, about ice, about snow, but I'm not quite sure it's the main interest for you doing geomorphology in Indonesia. So I will leave out those elements, and we will be talking mostly about elements that are important. And when you can think about Indonesia, like the place where I am now in Japan, one of the essential parts is tectonic. We are unfortunately in two countries where the the active forces come from plate tectonics, so that we have a lot of earthquakes, and based on those earthquakes, then landforms are created. So it's one of the major agents in earthquakes. Oh, hold on a second, someone is knocking at my door and gone. Good. So today I want to, can I, yeah, today I want to talk to you about tectonic geomorphology. And as you can see, I will try to speak as slowly as I can so that we can all understand each other. The video is being recorded, so if there is anything that you don't understand, my English was not clear, you couldn't understand the word, please don't worry, you can then watch that video again and listen to it again. So today's organization of the class, what we'll be doing. First, I will be talking to you about elements such as uplift and erosion rate after a short introduction. And you're going to tell me, well, erosion, it's not tectonic geology or geomorphology. Well, tectonic activity is being balanced. It's in balance with erosion. So you cannot talk about one without the other. It's important to talk about the two together. Then we can talk about some of the elements that control the seismic activity, stress, strain, and also their manifestation. One of the main manifestation of stress and strain are faults. Right now, if you don't know what is stress, what is strain, well, you will know in a second. Wait. And finally, I will talk about paleoseismicity and event in the landscape and how we can look at those. And we will finish that lecture with an example from the work of Dr. Saputra. Excellent work, amazing work from Dr. Saputra about faults in the Bantul area. The objectives of the lecture. I want you to be able to understand the tectonic processes that operate on the landscape. You will also know the link between tectonic processes and the landscape, and you should be able to examine, look, investigate a landscape in front of your eyes and know whether you have tectonic activity or not at all. It's not going to be a silver bullet, but as a geomorphologist, it's very important that you know how to read the landscape. And hopefully you can learn some of those techniques today as well. So Let's go back one step back and think about landscape evolution. I was telling you that tectonic is balancing the forces from erosion, which is all great. But those ideas didn't appear straight out of thin air. We had a progression of ideas, people thinking a lot of crazy things about geomorphology, about how the water is moving. To just give you an example of something that was a bit older than this, before the European, in Europe, the French, they were thinking that water in rivers, they were not coming from rainfall. It was somehow the seawater going back and up in the mountain and then flowing back. When you hear about it today, well, that's crazy. It's not possible. But people, scientists, really thought about it like, why is it that rivers are flowing? And it took some time for them to put two and two together and think about, oh yeah, it's raining and rain, but where does the rainfall comes from? And that was another question that got scientists to think for a long period. That was long, long, long ago. You could go back and think about a time where we all thought that the Earth was flat, or at least the European thought that the Earth was flat. Now it's very different. And if we zoom to the 19th and the 20th century and the beginning really of geomorphology, we have the start of some of those ideas and thoughts. And I've put on that slide three major ideas, three major thoughts that come through geomorphology. The first one, it's a name that you want to remember. Someone very famous in geomorphology is Davis, William Morris Davis. William Morris Davis was born in 1850 and passed away in 1934. His theories are very well known. They are known as the division theory. And the way he was looking at the landscape, he's an American scientist, was separating two processes. There were first uplift process creating the landscape, and then the uplift will stop. The tectonic, now today tectonic, they didn't know at that time about tectonic, but now we know about it. But the processes will stop, and the processes that made those landforms will slowly be eroded. So you will have first a raise, peak of a mountain, and then slowly erosion. Remember, at that time, the tectonic activity, the earthquakes linked to tectonic and landforms, this was not on the table. People didn't know about it. They didn't think about it. They thought about different processes on how the landscape were created. I don't want to put too many of those old ideas in your mind because it may be not the time to remember them. But ideas were very different. And then based on that, you have another group of theory which is challenged, or not challenged, but promoted by Walter Penck. He's from Austria, and Penck's idea was rather similar with times of like growing relief and then declining relief. But we didn't have this very clear division that Davis had. And then later on come John Tilton Hack, which is much more of a contemporary way of looking at our geomorphology. And I will let you discover his theory on your own. But if you remember only one person, remember Davis. Davis is really the key, the very beginning of geomorphology. Now, when we look at this very thin crust, this very thin area that we are interested in as geomorphologists, we have to remember that it is the result of a construction of huge scales. If you look at the graphic in front of you here, those images, look at the scale of the Earth and how the scaling of this element and that small element here scaled up shows our mountain so tiny, small little thing compared to the Earth's scale. This division, this dichotomy in space also exists in time. The time we look at when we look at geomorphology is a very tiny portion of the Earth's history. A lot of things we cannot even imagine, I think, have occurred on the surface of our planet, and we just don't know it. So remember, when you look at geomorphology and you look at geomorphology in time, you look at a very small slice of the Earth's history and a very small slice of the Earth's planet as well. But this being said, this very small slice is where we live. Without it, there is no human being. Without soil, without geomorphology, there is no mountain, there is no trees, there is no animal, there is no life on Earth. This boundary layer, even very tiny, is arguably the most important one. And today, especially in USA, in America, people are calling this layer the critical zone. So this is another example of the scale at which we're looking at. Now, this huge planet, which is a huge engine, is creating a lot of energy. There is a lot of energy. It's not creating. There is a lot of energy inside. And that energy is moving the surface. This is the plate tectonic. I'm sure you have heard from it in other classes. But when it comes to geomorphology, there are very different ways to see that this plate tectonic movement is existing. And on this slide, what you can see is a series of raised beach ridges. Can you see them here? This one here, and you have another one here, and a third one here. So you have 3 beach ridges next to one another. And this shows one thing. This shows that the sea was connecting to those beach ridges before. But obviously, the present sea level is different. We could explain those beach ridges with 2 different ways. We could think, okay, we have climate change and the sea level has gone down. So that the sea level is much lower today and it was connecting to beach ridges that are much higher today. That could be one possibility, but when we look at the way they were built, the order of those, we know it's not working there. The other possibility, the other solution, which is the right solution here, is that tectonic activity has pushed the land up. And as the land goes up, then you have different water levels that connect to the land, and that connection is being recorded. And recorded is the very important word. If you are here listening to me, all young geomorphologists, remember the surface of the Earth is very dynamic. It's going to actually show a lot of changes. Record those changes. If you look at the photograph, you can see that you have some movement here and there is a cone or the talus showing sediment movement. A lot of that is happening. But at the same time, while you have events that erase the past because they modify it, you have also a lot of hints, a lot of proof of past activities. And as a geomorphologist, you can use those hints, you can use those elements that you find in a landscape, a bit like a detective story. trying to patch and build together how was the land before, how does it evolve, what are the processes happening there. And in this case, when you look at this photograph, you know that something has happened. And you know that this something is the land and the sea not connecting at the same height at the same time. And because of it, you can start thinking, okay, then what happened? Sea level rise or tectonic activity? And then you do some field investigation, which is not the goal today. And you discover that the older ridges are right there, and those are more recent. This one is more recent. So you know that the land has gone on the up, or the sea has gone progressively down. And in that case, we know that it's tectonic activity because within the short time range, the sea hasn't moved that much. The sea was constant. So the only possibility was really to have the land going up. So uplift, erosion are essential questions, essential topics for geomorphologists. And that's what we're going to start with. We're going to start with uplift and erosion rates. This photograph here that you can see is Pas Gempa Bumi in Indonesia. So it looks maybe familiar. It is familiar. It is in Indonesia. So those were the examples that we saw first. Let's look at another set of examples. Let's think about what happens when uplift occurs near a river. When you have surface uplift, you have rock uplift plus deposition minus erosion minus compaction. A lot of words together. Let's look at the photograph or the pictures together so we will know it a bit better. Let's start with A. So with A, imagine that you have a river with hill slope on the side, and the river is eating down those hill slope. The size of those hills is related to the river eating down the sediment and the mountain. So the more the river is incising, the more the river is eroding, the more the slope around it are trying to connect to that river and come down. But the river itself is not flowing there by any chance because it's just there. It's flowing to a base level. It's flowing to the sea level. So if you have uplift in the mountain, so imagine that my arm is the mountain, this is the sea level, uplift is occurring. So because uplift is occurring, then the river is flowing faster and faster, in which case it's eroding more. So what is happening is that the original slope are lowering as well because they are trying to meet the river level, and you have increased river incision. On this graphic, you have two, you have B and C, because this process of having the slope and the river being balanced can lead to two different patterns, not only one, two different cases. The first case that you can see in B is when the hill slope lowering, the rate of hill slope lowering is faster than river incision. Imagine that your river is on a hard bedrock or on concrete, and the slopes are made of very tiny sand, not consolidated. Then you're going to have eventually badlands, for instance, but you're going to have a lot of erosion very fast when the river is not going so fast. And the result will be in smooth hills. The river level and the hills will not be that differentiated. On the opposite, if the hill slope lowering is much slower than the river incision, so that the river, let's say it carries a lot of boulders, sand, and gravel, so it erodes when it transports the sediment. It erodes very fast. In that case, the landscape is going to be very steep, and the river is going to be very deep. You're going to raise your hand and tell me, oh, Chris, this is very interesting, but it's not about tectonic. Where is tectonic geomorphology here? Well, this is also tectonic geomorphology because the river and the slope are reacting to the uplift. This process here is balancing the uplift. So if the uplift is very quick, you will have something when the case of the river incision is fast enough and faster than the hill slope lowering, you're going to see type of landscape. So next time you go around, let's say, Baron area or the south of Yogyakarta, having a bit of fun, look at the shape of the slope. Is the valley very thin? Is it very wide? Or is it very shallow hills? Or if it's very steep hills? Those will give you indication on the different rates of the processes that act on those different areas. And all of that is controlled by the balance of uplift and sea level movement. If we keep the mean sea level level at the same for simplicity, the only thing that controls the A, the B, and the C, it is the uplift. So it is tectonic geomorphology. So I'm mindful of the time, so I will go to the next slide. I will let you discover on your own the explanation which is underneath. More or less, it is saying the same thing that what I was telling you. Now, if we continue on uplift and erosion rates, from the previous graphic that I was showing you in the case B and the case C, it ensues that you have different mean erosion rate and mean relief construction in kilometers, meaning that the bigger your relief, the higher your mountain, the more erosion you have. So now, if you bring that together with uplift, it means that if you have a lot of uplift, you think about Himalayas, or you think about South American mountain and the Andes, very large mountain, very big, but it also means a lot of erosion very fast. Small landscape, small relief, less erosion. And this graphic is showing this. You see if your height is very low, you will have relatively small erosion. And the more you go in large relief, you're going to have larger amount of erosion. These data sets are for North America. If you go to Indonesia, if you go to Japan or Taiwan, the rate is going to be different. This curve here, this line, will be a bit more straight this way. Because even if the mountain is a bit smaller, you have a lot of rainfall, and then you're going to get a lot of erosion. Okay? And it means that the erosion rate is related to the slope. If the slope is very steep, you got a lot of erosion. And this is what the graphic here on the right with the blue dots is showing. The higher the slope, the higher the mean erosion rate. Now, one word of warning, be careful. One word of warning, be careful about this data because very steep slope, very, very steep slope. If the mountain is not like this, but very, very steep, like this way, you have less erosion. Why is it that you have less erosion? It's because on very steep slope, you can only have hard rocks. Anything which is sediment or easy to erode is not going to stay. So you have low erosion rate. So the graphic goes up, very high erosion rate, like you can see here, when you have strong slope. But if you go to 40 degrees, 45 degrees, then you go down again. Your erosion rates go down again. To have erosion, to have a high erosion rate, you need a slope which is gentle enough for the soil to develop on it. If your soil is not developing on it, there is nothing to erode. And those graphics, the other graphics show similar elements. Now, as a geomorphologist, what I would like to know is like, oh yeah, Chris, theory, very interesting. Maybe it's good for a book, but how do you do it? How do you measure the erosion rate? Like, I love GIS. At UMS, I've done a lot of GIS. How do I measure this erosion rate? Well, it's not very difficult. The way it works, you can see it in graphic A here. You have in yellow and in blue today's topography with a lot of giza-giza. Giza-giza is in Japanese. It means a lot of up and down, up and down, up and down. This is today's topography. And you can see in orange here are the zones we think have been eroded. So on that graphic, yellow and blue is today topography. And in orange or pink salmon, it's a weird color, we have the eroded volume. So the way we do it is we take a topography. Look at the one on the right here. This is a two-day topography with different wind gaps and water gaps. So it has been eroded. And from that, we create a smooth topography. We create actually a line like this dotted line here that link all the top ridges and ignore the valleys, ignore the cracks, ignore the fissures and everything which is linked to erosion, and we measure the difference of volume. So when we do the envelope here minus the topography, then we get an idea of the erosion here. This erosion is the product of uplifts versus the erosion forces. If you don't have uplifts, if you don't have tectonic, then the landscape become old and smooth and disappear. But because in Indonesia you have constant tectonic uplift, you have volcanoes. Volcanoes is another lecture, but you have volcanic activity. Think about Merapi, think about Semeru, that bring, or any other volcano, that bring a lot of material at the surface that create a very smooth topography like this. You know, like an ice cream. When you look at Mount Merapi, it really looks like an ice cream. And then you have the monsoon period, and during that period you have a lot of lahar, a lot of banjir, and this is going to erode the material. To know how much material was eroded, we do this envelope minus topography equal erosion. And we know that the amount of erosion, how much sediment come out, is directly linked to the uplifts, directly linked to the volcanic activity. So this is another example here where you can see the present topography that is in California, and this graphic here is showing you actually, this graphic here is showing you how much erosion you had. So, as a geomorphologist, when you're going to be fourth-year student or doing your project, if you do a project in geomorphology, you can think about the amount of sediment eroded and transported as a proxy of uplift. Depending on how much sediment is being exported, you can tell whether it's being active or not. Now, I talk about activity, about mountain building, about a lot of different processes, but how does it happen? What are those processes? Oh, hold on a second, there is a chat. It's okay, there is nothing in the chat. Not so important. Sorry, I was wondering whether it was a question. So, stress, strain, and fault. And how does it happen? So, quick overview. We have the mantle. On top of the mantle, we have different tectonic plates, and they go converge towards one another. They diverge from one another this way, depending on where you are. It's not the goal of this is not a geology class, so I will let you look at those slides later. But just remember that you have plate tectonics, you have margins, and those margins are very active. And when you look at Indonesia here, you can see that it's one of the very active margin. And so is Japan right there as well. So we are in very similar country, actually, when it comes to geomorphology and geology. And at those margin, the tectonic activity is going to create a lot of different type of landforms. And you have joints in Indonesia or in Japan that are convergent, going towards one another. And you have some that are divergent as well. And those that are divergent also look like this. So it doesn't mean because you have divergence that you have no activity. You have a different type of activity as well. And most of it is being hidden underneath the sea, so we don't see it so much. And here is a general map where we map and the volcanoes and those activities. So that you can see the Philippines, Indonesia, Japan, all very, very active area. Very interesting to study geomorphology, actually. Now, when you look at faults and you look at fault stress, what is happening and how does it work? So look at A first. Imagine you have stress which is pushed in the X direction, so horizontally, and you have stress which is in the Z direction. Right now, I'm not looking at the Y direction. I forget Y direction. Just think X and Z. And the way to look at this graph, the size, the length of this arrow is very important. When the arrow is very long, it means that we have a lot of stress in this direction. We can push or stretch a lot in this direction. When the arrow is small, very tiny, like the arrow in X here is quite small, it means that the stress in that case is small. And when we have a normal section, a normal fault, one of the process that we're going to see when we have stretching, we are going to have faults that follow that movement. So the stress on those faults is going to be mostly vertical, a lot of vertical stress, very little horizontal stress, and it can lead to a block which is going down. We are going to see one example later of this kind of fault where the block is going down. Another example this time is the opposite. When you have the stress, vertical stress, which is very, very small, but the horizontal stress very strong, very big, then in that case, you have a different pattern. You're going to have faults that open this way and that will push towards the center. In those examples, I have two faults facing one another. A lot of times you will only have one. Here I just put two to show you that the direction doesn't really matter. And when you look at a strike slip, this time we are not going to look from the side. We are not going to look at a transect. We are going to look at it from the top, like as though you have a map. That's why it's written a map view. When you have stress in X and Y that are quite similar, you're going to have more complex movements that show complex shear like you have here on this type. And block will move past one another. So the block will move together this way. A and B blocks move mostly like this. C block moves like this. Now, when you look at the strain accumulation, so what is the strain accumulation? It's the amount of potential movement which is accumulated near a fault plane. When you have horizontal displacement and the position of the plane, you have a positive and a negative direction, and the location of the fault plane is the place where the positive becomes negative, so you have an inversion of it. So it is sometimes not very intuitive, so the best is for you to look at the graphic and try to picture them in your head in terms of forces and movements going one against another. The U here is going to be the movement, the direction of the movement. The UX is in X, UY is in Y. So when you have an earthquake slip, when those movements are created by an earthquake, what kind of stress do you get? Do you have just a linear stress? You know, in the previous slide, I was telling you we have in X and Y different level of stress, but this stress is not being constant. It's not always continuous the same. It's going to change. And it changed also during one single earthquake. And when you are facing actually earthquake, you're going to have actually different level of stress. The first model, and we are using model because we don't know really. We think it works this way, or we think it works this way. Of course, it is based on data. Of course, we are using data to show and prove those models. But the fact that we have different way of thinking of it show that there is no one single solution. So over time, when you have like in A, a stress which is going up, and then after an event, you have an earthquake, and then goes down, then up again, then down and up and again, all constantly. So between the stress level 1 and 2, you don't have actually much changes. The amplitude of the stress is going to be quite the same. In that case, you're going to have a constant slip rate. Each time you have an earthquake, it's going to move about the same level. Because the stress is the same, the force, if you look at it from an area on your fault, is going to be quite the same as well. So there is quite something which is regular, like a constant way of moving. Another way is when one of the stress is quite constant, but the lower amount of stress varies. So we know that it needs to reach a threshold when it is at this threshold here. When it is at this threshold right here, you know you have an earthquake, but the in-between earthquake stress level can go down to different levels. So the earthquake is kind of predictable. We know that you need to reach X amount of stress to get the earthquake, but in between the stress changes, so it's really hard to know when it's coming back basically, unless you have the stress data. And you're going to have a somehow constant slip rate based on those. The other the C model, which is the slip predictable model. This one is a bit more complicated in the sense that it's the second value that we have. And in that case, the prediction will be mostly based on the return of the stress to a level 2. And then we have the more complex model, which are the clustered slip model, where you have actually, that's why they are called clustered. You have different wave amplitude and wavelengths that are mixed to one another. In that case, you're going to have long-term slip rates, short-term slip rates, all mixed together. You see this line here, the line is jagged. So it means that you're going to have small earthquake and then a big one, and small earthquake and then a big one. So you're going to have like slip that goes small movement, then big one, small movement, then big one. And of course, it's not always constant. So there are a lot of different types of slip. And different type of slip mean that, remember the erosion we talked about? Remember about the river eroding? It means that the river will have period where it is going to erode a lot, and then it's going to deposit sediment, and then it's going to erode again. So things will be not linear. It's going to have acceleration, and then slower erosion, acceleration, and slower erosion. Now, if you look at your fault in space, you're going to have different type of space model. So when you look at the distance along the fault, so you imagine the fault as being a line, you have places where you're going to have a lot of movement and places where you're going to have less movement. And the distribution, the spatial distribution of this movement will be either, like in A here, variable. So it means that the place where the big movement occur can change, or it's going to be uniform. It means that every time more or less the big movements occur at only one location, and then you get adjustment. Or even more simple, you're going to have only one type of movement, one single way the fault is acting. It's always here that you have big movement, and it's always here that you have small movement. So you have here the cumulative slip. You can see on A, it's moving here and there, very hard to predict, very variable. Then you have B, which has constant displacement by event. And you have C that shows always the same type of displacement. C is most likely not to occur in a lot of cases, and C is most likely to occur over short periods, like let's say 100, 1,000 years. But over time, as the fault change, as the landscape change, you move towards B or A type of movement. And on the right, you have for different faults in USA, the maximum fault displacement. And you can see that depending on the type of fault that you have, the places and where the movement is occurring is going to change along the fault. And the cluster, you can see the red point, you can see the blue point, the black point. Those show normal fault, thrust fault, and strike slip fault. And depending on what type of fault you have, then you're going to get different places where the movement occurs along the fault lengths. And we're going to look at it in more details now. Sorry, I stopped the air conditioning. So when you look at this series of fault here that I give you as an example, it's very, very interesting that both at the 20 to 100 meter scale, A, 400, 600 meter scale, B, 700 to 200, 2,500, then all the faults together, what you can see is that regardless of the size of the fault, most of the time, the maximum movement will be concentrated in the center part of the fault. How do you read that graphic? You can see here you have 0 to 1, 0 to 1. What is that? It says the normalized distance along the fault. It means that we have taken the fault line, let's say 400 meters, and we have divided that distance by its own length. So all the faults now measure 1. It's not 1 meter, it's just 1. There is no unit. All the faults are normalized, the fault lengths are normalized. And on the y-axis here, you have the throw. So how much throw you get. And this time you have a length, and it's in meter. It's L in meter. And for different throw, we have different curves. Let's say when you have a throw L of 24 meters, 55, 60, 167, 180. So it means that we look at one fault and we look at many movements. It moved many times, and each time it moves, it's very funny. The distribution of the movement, the location where most of the movement occurs, is going to be invariably in the center part. At the edge of the fault, you have less movement. Whether the earthquake is big, it's small, it occurred Monday or Wednesday, the fault is long or is small, you always have the most of topographic change. The geomorphology is going to change the most in the center part. Now, if you look at the photograph underneath, look at this fault here. So here you have a fault, and the center part has moved a lot, but on the side, less movement. Look at the fault at the back. The fault at the back, where it says normal faults. It is the same. You have a big center, and then it does one length towards the end. It's cool, right? Regardless of what faults, what rock you have, whatever you have, you always get the same pattern, which is really funny. And this pattern applies to one fault, but also to a series of faults. Look at the document on the right. Look at A, B, and C. A is showing you what I was explaining just now. You have one fault at T1, T2, T3, and while it moves, it's growing. But when you look at B, with the fault which are also growing, you can see the same pattern than in A, where the growth and the movement vertically is faster in the center. And when you have what they call here early propagation and restricted, you get something similar as well. The shape is going to change because on the side it's restricted, so the fault is not going too much on the side, but it's going to still continue going up or building up more in the center. Okay, so it is very important. When you have one fault, it's going to grow more in the center than on the edge. When you have many faults, it's going to grow more in the center of the mini fault and less on the edge. And let's say on the side you have some volcanoes or something blocking the fault, stopping the fault. You still have the same pattern, but in the center, it's going to grow faster. It's going to actually have a bigger propagation. How cool is that? And this is another example of what we were talking about. You have here a set of faults in the US. It's in California, actually. And this set of faults is also growing, showing the same pattern. Look at document B and look at faults A, B, C, and D in blue. All of these faults are showing the pattern we see here, where you have more change in the center, less on the side. Individually, the model works. And on top of it, the whole group of faults are moving more in the center than on the edge. And this is going to control the geomorphology, the tectonic geomorphology, and the shape that are created by those faults. And when you link all of that back now to geomorphology, to the landscape, to the shape of the Earth you are more used to, I'm using in that slide a document, the references at the end for all of this. In that slide, you can see actually how the fault and the fault movement then relate back to the different landforms. And this is a zoom of what we were looking at. Beautiful, isn't it? Can you see how the tectonic is controlling the geomorphology? And this is typical tectonic geomorphology. But if you want to see that, if you want to understand the tectonic geomorphology, what you're looking at actually is erosion. It's the erosion difference between two different elements. And those are some more examples. So earlier I was talking about stress, about strain, and maybe you got lost a bit. And I was like, not my thing. This is another way to look at it. Now that you have seen all of this, those faults can be created by either tension and stretching, compression or shortening. Can you remember the image where I was showing you from the map view? It's the same concept. Side view, and the top we have the shearing with the top view. And when you mix all of them together, like here we have shearing, we have a compression, you're going to have complex movement. And that's why when you think about your faults, it's not only a fault, you're going to have also folds coming with them. And folds creating syncline and anticline. So in geomorphology, the syncline is when the geological strata follow the topography and are inclined like this, creating a hole, basically. It's not a closed hole, but a syncline. And when it's going up, it's called an anticline. And when you have a hole in an anticline, it's going to be called in that case a syncline ridge. My advice is that you take a dictionary, you learn those words, learn it in Indonesian, Bahasa, and you learn the meaning of those words together. And those are some more examples of the different shapes of the fault. So this I will let you have a look at it later. And this is an example from Sumatra as well. It's already almost one, so I will go quickly through those so that we can look at not Borobudur, but paleoseismic and event. Okay, so paleoseismicity and events. We go back to our first slide, our first element. And I was telling you, how do we know how the landscape has changed? Then to do that, we look at paleoseismicity. It means that seismicity that happened in the past. And in that case, I was telling you, how do we know in what order things came first, second? The scientists who did that research here in the lower part, they found a Coke can. So that we know that Coke can is not that old, because it came with the sand that created that ridge, and that ridge was created in the 1960s or 70s, whatever the Coke can dates back from. So using different hints, different elements, we can reconstruct the evolution of the landscape. And when we do that in more detail, this is another example in South America, we can look at series of ridges, like here. And those series of ridges, we can date them. We can use stable isotope or isotopic dating. And using those isotopic dating, we can know what order those different ridges were created in, and use that to reconstruct the evolution of the landscape and also know how fast the topography is moving. So for each ridge here, you have this elevation data here. So the yellow one is the highest one, and those red and orange one is the one closest to the ocean. So the ocean is here, and the ocean being here on that location, you go up, you have the low topography, which is here, and then you go up and go up and go up, and you have the highest ridge that extends from 4 meters to 7 meters high. What does it show you? Well, it shows two things. It shows that the land went up, okay, but it also shows that the land didn't go up all at once in one direction. Actually, there is one location when it went up very fast, and faster than the other side, which is really interesting. And once we have all of that, we can connect them to the dates, and connected with the dates, we can have an idea of the rate at which the landscape is changing. Another way of measuring how the coastline is changing and how the landscape is evolving because of tectonic activity and seismicity in the past is to look at paleosoils and paleovegetation. And one example that you have here, I know some of my colleagues did some similar work also in New Zealand, where they look at paleosoil that are buried and new soils on top. And those differences show you that the ground level was much higher before, and then it goes down and goes down. If you think about Banda Aceh in Sumatra, before the earthquake even, in Banda Aceh in Sumatra, when you go to the port, at the bottom of the port, you have a 13th century cemetery with tombs that are Muslim cemetery. And the Muslim cemetery was in the port. The reason because of that is because the land is going down. And as the land goes down, unfortunately, so went the cemetery as well. So this is another element you can use to measure the activity. And I will conclude today with a very good paper by your professor, Dr. Aditya Saputra. It's a very, very good read. I suggest you go and read it. It's called Preliminary Identification of Earthquake-Triggered Multi-Hazards and Risk in Pleret Subdistrict. It's a very long paper. He did a lot of work. So we are not going to look at the hazards, but just look at the start and the geomorphology of the fault. And he has done beautiful graphics, so I'm using them right there. So this is also a map that he created. And as it says, it's a figure 1 of his paper. It's called the segmentation model of subduction earthquake sources in Indonesia. And he used data from Israel et al. In 2012. And one thing you can say is that Indonesia is riddled with earthquake and strong earthquake. So it means that faults and fault movements are a major agent in controlling the landscape and the landform formation. And then it zoomed to an area which is the area of Bantul. that you have here. So you can see his beautiful skill in GIS as well. As a geographer, hopefully you can develop similar skills yourself. And in the Bantul area, he has done a transect A to B, where you can see very clearly the high area, the low area, and another host. And here he has put the opaque fault, which is right there. So remember what we were talking about, the level, the block going up and down. And how do we know it? Well, look at your topography. You have the Bantul Graben, you have another host over there, and you have the opaque fault, which is right here separating the mountain on that side here. And he focused on this area to look at the opaque fault. And what is really interesting when you look at his map here, what you can see very beautifully, you see the river, how it's going to be 90 degrees or 45 degrees angle in one direction, then one direction, then moving again, then moving again. This is typically the kind of movement that river do when you have a fault. So when you are doing your detective story as a geomorphologist, you look at the mountain, you look at the shape of the landforms, but you also look at the shape of the river. And if you look on the left side, look at this one, it's beautiful. You can see it's going down and patching, going straight at an angle. So all of this shows the presence of fault. There is a lot of research to be done in those areas because you have Merapi volcano. Merapi volcano creates a lot of sediment. So it feels a lot of the changes and the small fault, and it's very hard to find them. So it's really a hard detective story that you need to be done. And another tool that Aditya Sapotra is known for, and maybe is going to teach you as well in the future, is the creation of 3D imagery using photograph, so using UAV or using cameras on the ground, so that you can reconstruct where the fault line is and what are their shape, so that you can have an idea of what kind of movement has been happening. And you can see here, if you have the fault, it's really beautiful. And you have some form of movement around here as well, showing that when the fault is moving, the other layers are also moving at the same time. So today's lecture about tectonic geomorphology is a lecture for Indonesian students, because tectonic is very important in controlling the landscape in Indonesia. Very often, if you want to put two main types of landscape, you have volcano-dominated landscape, and you have tectonic and the floodplain around dominated landscape in Indonesia. So, in conclusion, what do I want you to bring back home? Well, everything. I want you to learn everything, but let's put it in a few words. Geomorphology, it's only concerned with the small film at the surface, but it's the most important part of our planet for us to live on. It controls about everything. Think about hazards, think about disaster, but think about also agriculture, the construction of soil. So geomorphology is really important. And landforms that are created are actually the result of this battle between all the internal processes and the erosion processes as we have seen today. And very often, because we only live 50 years, 80 years, 100 years sometimes, we cannot see much of the tectonic change, but we can look at the erosion. We can look at the change in erosion and measure them. And using those tools, we can understand better the tectonic landscape. And finally, as I said, Indonesia is strongly influenced by tectonic forces due to its position. And for this reason, it is very important for you to be able to read those different elements. Next time, when you have your own life, you are outside university, and let's say you have a wife or a husband or a partner, and you want to buy a house, maybe one thing you can think about is like, is it safe? Is it on a fault line? Is it away from a fault? And try to think about what kind of measures, or should you be prepared to see an earthquake, for instance? So all of this can have a very strong influence on your personal life as well and what you can do across the country. But right now, there is not enough geomorphologists, I think, in Indonesia. We need to have more of them to come and study with Aditya Saputra, fault line, and the different hazards and disasters. All right, that's all for me today. Thank you very much. Thank you for listening.
Thank you very much, Professor Gomez. Do we have time for question and answer, Professor?
Yep.
All right. For all participants, do you have questions? Please raise your hand.